So let's talk about security. Security has been in the news a lot lately. There have been some really significant breaches of some really significant companies, which sort of demonstrates both the real importance of security and the fact that the standard practices in security simply don't work. If they worked, we wouldn't be seeing the sorts of exploits that we're seeing. And so I want to talk about security not from particular exploits, but from principles which would help us to then go on and create practices which will actually be sound and will be effective. It's often thought that security is a battle between people in invisible colored hats. There are the white hats who are supposed to be the good guys, and the black hats who are supposed to be the bad guys. And unfortunately, there are famous black hats who used to be white hats, and the white hats that used to be black hats, and there are gray hats who are playing both sides. It turns out you can't tell who someone is by their invisible hat. That this is a model of security which simply does not work. Security is not about hats. One of the problems with that model is that having specialization means that most people are not concerned at all with security. That the specialists worry about it and the rest of us are just trying to be productive. And that model definitely does not work. Security is everybody's job. Security has to be factored into everything that we do. One of the sources of insecurity is that things change. It might be that at some time, some practice might have been okay, because things were limited in size or scope or reach, but then it gets put into a larger context, and then suddenly it's not secure anymore. It is not unusual for the purpose or use or scope of software to change over its life. Rarely are the security properties of software systems re-examined in the context of new or evolving missions. This leads to insecure systems. Do you know who wrote that? I did. So we're going to talk about principles, because tricks and hacks do not work. If anybody tells you, here's a trick that's going to make it secure, they're either misinformed or lying, because that is not how security is obtained. So first principle, deterrence is not effective. Deterrence is effective in the real world. That's why we haven't blown it up yet. But it doesn't work in a computer network, because you can't punish an invisible attacker. The attacker doesn't even need to be awake while the attack is going on. So intimidation doesn't work. The only thing that works is prevention. I want to introduce you to this guy. This is August Kerckhoffs. He is a Dutch linguist. In 1883, he wrote the first modern book on cryptography. Prior to Kerckhoffs, cryptography was the science of secret codes written on paper. But Kerckhoffs re-examined cryptography as a result of the telegraph, which was used for the first time in war in the American Civil War. And he observed that that really changes everything. And so he came up with a new theory of cryptography based on electronic communication. And he got a lot of stuff right, which is kind of amazing considering how long ago he wrote it. It is still relevant. The things that he developed still work. The thing that he wrote that is most quoted is called the Kerckhoffs principle, which is the design of a system should not require secrecy, and compromise of the system should not inconvenience the correspondence. So let me demonstrate what he means by this. So we have two correspondents, Alice and Bob, and they want to be able to communicate, but they don't want anybody to see what they're saying. So they use a cryptographic system. Alice has her plain text, her message to Bob, that she puts into an encryption machine along with a key. That produces a ciphertext, which she can then transmit to Bob. Bob receives the ciphertext, puts it in his decrypt machine, which may be identical to Alice's machine, along with a key, the same key that Alice used that they exchanged in a prior meeting. And that allows him to recover the plain text. This is how pretty much all cryptographic systems work still. What Kerckhoffs said was there should be no secrets in the encryption box, that we should assume that the enemy knows everything about how the encryption box works, that the only secret in this system is the key. I still see a lot of experts who get this wrong, who think we should try to hide as much of this mechanism as possible in order to slow down the attackers. But Kerckhoffs told us over a century ago that that doesn't work. So one of the corollaries of his principle, is that there is no security in obscurity. It turns out that the more secrets you have, the harder they are to keep. And just keeping the keys secret is really hard. All of our focus should go on that. And we should have confidence in the encryption system that it requires no secrecy. Some people take this so far as to say that we should publish all of the details for how our systems work in order to keep ourselves honest about having no obscurity in our systems. So cryptography is not security, but there are ways that cryptographers think about security which could help us to think about security. So I'm going to teach you to think like cryptographers. And I'm going to do that by introducing you to an algorithm called the one-time pad. This system is guaranteed unbreakable. In all the other cryptographic systems, there's a fixed length key, and a brute force attack will eventually work. You know, if you have enough computers and enough time, eventually there's no system that can withstand breakage except for this one. You can have all the computers running in the universe till the end of time, you'll never break it. So it comes with some rules, as does every cryptographic system. So rule number one, the key must always remain secret. That's going to be true of every system. Rule number two, the key must be at least as long as the plain text. This is a really unusual requirement. Most systems have a short, fixed length key. This one says the key is the same size as the message you're trying to encrypt. And then rule number three, the ciphertext is obtained by exclusive OR of the plain text in the key. That's the algorithm. This is also maybe the simplest cryptographic system. So let's demonstrate it. So this is my plain text. Usually you think of plain text as being text, but you know, this is a picture. And each pixel is a number, and that's what we're encoding. So this is my key. It's just random noise. And I went to some trouble to pick out some really good random numbers for you. And if I exclusive OR these two things together, the signal should be completely hidden in the noise, right? There shouldn't be any whisper, any ghost, any reflection, nothing. There's no sign of the original message in the ciphertext. If you can't see anything, then I encrypted it correctly. Then the next rule is the key must be perfectly random. So I think my key was pretty good, but let me show you what happens if you have a bad key. So this is a key, looks just like the first key, except I made this one in Photoshop using one of their noise filters. And while it looks to us to be sufficiently random, it is not perfectly random or cryptographically random. So if I exclusive OR my message with that, you can see it, right? So understand what's happening here. You are breaking an unbreakable code with your brain. And you're not even working hard doing this. You're doing it because your visual system is extremely good at separating noise from signal, and that's what you're doing here. And so if any signal manages to leak out, any redundancy, anything, you're able to see that. This is the same kind of analysis that cryptanalysts do when they're looking at a code. They're trying to find, is there any information which is somehow leaking out that we can use to break the code? Then the final rule is so important, it is the name of the system. The key must never be used more than once. So the operational metaphor was, I print two identical books of random numbers, and I give one to you, and I keep the other one. And when I want to encrypt a message, I will pull out the top page, I will encrypt with it, I will then destroy it. And then when you receive the message, you will take out the top page, and you'll decrypt with it, and you'll destroy it. We have to be confident that the key will never be used again. So let me show you what happens if the key is used again. So here's a picture. I'm in Istanbul, by the way. And you'll remember this is the first key that I showed you. You recognize it, right? So I'm going to exclusive OR them together. And again, you can't see it because it's a good key. But now I'll exclusive OR the two ciphertexts together. And what happens is the keys cancel out. And there's no security in exclusive ORing two messages together. So cryptography is not security, but there are things that cryptography can teach us. So when cryptographers are looking at a system, they have a cast of characters who they employ to help them reason about it. So we've already met Alice and Bob. These are two correspondents who want to exchange messages. There's also a character named Eve. Eve is an eavesdropper. Eve might be the NSA. Eve has a packet sniffer, and she's looking at all of the traffic going between Alice and Bob, hoping to accumulate enough information or enough metadata that eventually she can figure out what they're saying. Then there's Mallory. Mallory does man-in-the-middle attacks. Mallory might be operating a public hotspot, in a coffee shop. And Bob wants to connect to Alice, but he's actually connected to Mallory, and Mallory connects to Alice. So Bob is trying to log in. Alice asks Mallory, what's your password? Mallory asks Bob, what's your password? Bob gives his password to Mallory. Mallory gives Bob's password to Alice. Mallory tells Alice to change Bob's password. Mallory tells Alice to transfer Bob's funds. Mallory tells Bob, we're down right now, please come back later. Is this something we should be worried about? Yeah, we should be worried about that, yeah. So in my own practice, I have another character who I call Satan. Satan is very smart, well-financed, well-equipped, and totally malevolent. He wants to hurt us and our customers. He wants to take as much from us as we'll allow him to take. So people are worried about him because he's not someone who's necessarily in between. He could be a customer. And so one strategy is we will not allow anyone to connect to us who is Satan. This is called a blacklist, and on the internet that does not work because it's so easy to generate new identities. So another approach is we will allow anybody to connect to us who is not Satan. That's a whitelist, and it turns out that doesn't work either. The only thing that does work is recognizing is that Satan will connect to us. And we have to design our system so well that no matter what he does, he cannot cause harm to us or our other customers. That is the only thing that works. And that's why security has to be factored into everything that we do. Security must be factored into every decision. In programming, we're making lots of decisions, maybe thousands of decisions a day. It turns out all of those decisions may have security implications. And so we need to be working with a set of principles which allow us to make correct decisions. This used to be a source of insecurity. We'll put something together and someone will warn there might be a security issue and a manager will say, well, we'll go back and make it secure later. We think the hard part's going to be getting the machines to boot or getting the boxes to talk or getting pixels on the screen. Once we get that to happen, 2.0 will go back and add security. And it turns out that doesn't work. You can't add security. Just as you can't add reliability. You have to remove insecurity. You have to remove unreliability. You can't put a box in the middle of a flowchart and say that's the security box. That doesn't work. Having survived to this point does not guarantee future survival. The net has been under attack since its creation, and we're all still here, and all the businesses are still operating, but that is not proof that it's going to continue. The impossible is not possible. So we should not attempt any security remedies which in fact aren't possible. We should not waste any time on it. Any measure which is not effective is ineffective, and we should not waste resources on it. If only because wasting resources on that means we're not going to be spending resources on something that might be effective. Don't prohibit what you can't prevent. And the corollary of that is what you don't prevent, you allow. False security is worse than no security, because if you know you have no security, you'll be cautious. But if you think you're secure and you're not, you will be reckless. So that brings us to the web and the web browser platform, which is horribly insecure. It was not designed to be a secure system. It should have been, but it wasn't. We are still fixing it later after over 20 years. HTML5 made things worse instead of better by adding powerful new capabilities to the attacker without providing remedies for the existing weaknesses. And yet, it is still better than everything else. All of the other application delivery systems, including things that were designed after the web, still get this wrong. So one of the things that all of the other systems get wrong is a blame the victim security model. So if the system has to make a decision about security and the system doesn't have enough information to make a correct decision, it will ask the user. And it will ask the user in language that the user probably cannot understand. And if the user answers no, then the system will fail to work for them. And if they say yes, then it's their fault that their identity is compromised. That is not a credible model of security, but that's in fact how everything works, except for the web. The web doesn't do that. The web correctly answered this question, something that everybody else has gotten wrong since the beginning of computing. Whose interest does the program represent? It's always been thought that the program represents the owner of the machine or possibly the programmer who wrote the code, but that's not the case. The browser recognized that in this case, the program represents the website and that the website's interests might not be exactly the same as the user's. Everybody else got that wrong. But the web got everything else wrong. So there can be more interests involved than just the user and the sites. If somehow a third interest can get in there, they can cause trouble. A malicious party can do that by exploiting coding conventions which inject malicious code. And that malicious code gets all of the rights of the site. This is known as the XSS problem. And we'll talk more about that in a minute. But first, when people talk about security, usually it's really vague, saying security is important and you got to do stuff to be secure. Why? Why is it important? So let's look at a particular scenario. What can an attacker do if he can get some script onto your page? The attacker can request additional scripts from any server in the world. Once it gets a foothold, and it only needs that much code to do that, it can then obtain as many gigabytes of additional code in order to complete its attack. Browsers have a security feature called the same origin policy, which limits the ability of the browser to obtain data from another site, but it puts no limit on your ability to load additional code from the world's evilest website. The attacker can read the document. The attacker can see everything the user can see and things that the user cannot see, including comments, hidden fields, cookies. All of that stuff is visible to the attacker. The attacker can make requests of your server, and your server cannot detect that the request did not originate with your application. If you're using SSL, and you should, the attacker gets your secure connection. If your server accepts SQL queries, then the attacker gets direct access to your database. Now, if instead you have a tier which is concatenating together pieces of text that you got from the browser in order to make SQL queries, then you're only probably giving the attacker access to your database. And that's because SQL was designed to optimize SQL injection attacks. The attacker has control over the display and can request additional information from the user. And the user cannot detect that the request did not originate with your application. So modern browsers have anti-phishing Chrome. And unfortunately, users don't pay any attention to it. But if they are paying attention to it, in this scenario, the browser is saying, yeah, it's good, because the browser is only concerned with where did the HTML come from. The browser is not concerned with where did the script come from. And so that's bad. So knowing that, some sites, whenever something scary or important is about to happen, they'll ask the user to type in their password again, the assumption that the attacker won't know that, except that the attacker has control over the display. So the attacker can ask the user, what's your password? And the browser saying, so if you have a website which routinely asks users to type in their passwords in unexpected times, you're training your users to give up their passwords as soon as the attacker gets control. An attacker can then send information to servers anywhere in the world. Everything that it learned from scraping the page, by talking to your database, from talking to the user, all of that information can go to the most evil server on the planet. Again, the browser has the same origin policy, which limits the ability of a browser to read data from an evil site, but it puts no restriction on the ability to send all the data that you've scraped and stolen and send it to that site. The browser does not prevent any of these things. In fact, web standards require these weaknesses. If you were to build a new browser from scratch, if it did not subject us and our users to these hazards, it would not be standards compliant. Is this starting to worry anybody? Anyone feeling a little uncomfortable? The consequences of a successful attack are horrible. There's harm to customers, loss of trust, legal liabilities. There's even been talk about criminal liabilities as the result of negligence for allowing users to come to harm. We saw recently Yahoo lost billions in its valuation as a result of its security incompetence. So the attack that I just described is called the XSS attack, which stands for cross-site scripting. They wanted to call it CSS, but there was another abomination called CSS. So they called it XSS. And the name is wrong, because there's not a problem with cross-site scripting. We want to be able to do cross-site scripting. That's a valuable thing, to be able to have sites working together for the benefit of the user, in completing transactions or doing other work. That's something that's highly desirable that we cannot do securely today because the browser didn't expect that we'd want to do that. Also, there are modes of this attack which do not require participation of a second site. So the term cross-site scripting is wrong. The security expert who first identified this attack and named it did not understand what the attack actually was, but that name stuck. And so the security industry expects you to know what they're talking about when they're talking bullshit, when their stuff just doesn't make any sense. So cross-site scripting attacks were invented in 1995. We have made very little progress in correcting that problem. We've made some baby steps. There's content security policy and the iframe sandbox, which can work when they're used, but they're both off by default. And so, unsafe by default is not a good default. It turns out a mashup is a self-inflicted cross-site scripting attack. Advertising is a mashup. Yeah, and so the most reliable, cost-effective method to inject evil code into a page is to buy an ad. So why did this happen? There's not just one cause, there are many causes. First, the web stack is way too complicated. There are too many languages, HTTP, HTML, CSS, JavaScript, URLs, regular expressions. Each can be encoded, quoted, commented, and escaped differently, and they can all be embedded inside of each other. And browsers will do heroic things to try to make sense out of malformed content, which breaks all the security scanners. Then template-based frameworks are optimal for XSS injection. I hate templating for that reason, but HTML is such a horrible thing to work with. Templating is the best mode anyone's come up with for writing HTML applications, but unfortunately, it's inherently insecure. The JavaScript global object in the browser gives every scrap of script the same powerful capabilities. And yet, as bad as it is at security, the browser is a vast improvement over everything else. And that's why I think the web is worth saving. So it's not a cross-site scripting attack. It is a confusion of interests. The browser distinguishes between the interests of the user and the site, which is good, but it did not anticipate that there might be other interests represented. And that is the fundamental confusion. So within a page, interests get confused. An ad or a widget or an AJAX library, an analytics library, get the same rights as the site. JavaScript gets close to getting this stuff right. There are things that are clearly wrong in JavaScript, but I think the language could be repaired and could become a secure language. HTML, I don't think so. I can't see that happening. Also, the API that HTML provides to the DOM, or provides to JavaScript, the DOM, is one of the worst APIs ever imagined. And one of the things that's bad about it is its security model. If you can get access to any node in the document, you get access to every node and the network. So this stuff's not going to get fixed in a hurry. So in the meantime, it's up to you as developers to try to write secure applications on an insecure platform. And that's really, really hard. But there is hope in something called the principle of least authority, which says that any unit of software should be given just the capabilities it needs to do its work and no more. So capability is a thing which represents access to something. So in an actor system, the address of an actor is a capability. It means that you have an address to which you can send messages. If you don't know an actor's address, you can't send messages to it, you can't interact with it, and that provides security separation. It turns out the same thing works in object-oriented programming. A reference to an object is a capability. If we can control how references are obtained and managed, we can create a secure system. So let me introduce you to object capabilities. So here's an object. It has state and behavior, which are inside of its circle, its interface. Object A has a reference to object B, so an object can have references to other objects. Object A can communicate with object B because it has a reference. Object B provides an interface that constrains access to its own state and references. Object A does not get access to B's internals. This is why the model of object construction in which all objects are frozen is so good, because that's the only way in the silly language to get objects with this capability. Object A does not have a reference to object C, so A cannot communicate with C. In an object capability system, an object can only communicate with objects it has references to. It's as though there's a firewall between A and C, and that firewall is implemented at zero cost. An object capability system is produced by constraining the ways that objects can be obtained. A reference cannot be obtained simply by knowing the name of a global variable or a public class. In fact, there are exactly three ways to obtain a reference to an object: by creation, by construction, and by introduction. So first, by creation means that if an object creates an object, then it gets a reference to that object. It couldn't work otherwise. By construction means that an object may be endowed by its constructor with references. This can include references in the constructor's context and inherited references. Then the important case is by introduction. So here, A has references to B and C, but B and C have no references, so they cannot communicate with each other. But A wants them to be able to communicate with each other. So A sends a message to B, passing a reference to C as its argument. And now, B is able to communicate with C. It has acquired the capability to communicate. And that's why this is called the capability model. If references can only be obtained by creation, construction, or introduction, then you may have a system. And if they can be obtained in any other way, you do not. So one of the things we need to be able to do is to attenuate or reduce the rights of an object so that other objects can safely interact with it. Some capabilities are simply too dangerous to give to guest code or to third-party code. We can instead give those capabilities to intermediate objects that will constrain the power. For example, an intermediate object for a file system might limit access to a particular device or directory, or limit the size of files or the number of files, longevity, or types. Ultimately, every object should be given just the capabilities it needs to do its work and no more. So capability should be granted on a need-to-do basis, similar to the way we might grant information on a need-to-know basis. What we know about information hiding as being a good design principle, it turns out capability hiding is an equally good design principle. Intermediate objects or facets can be very lightweight, and in class-free languages like JavaScript, they can be very effective. So here the facet object limits the guest object's access to a powerful object. The guest object cannot tamper with the facet to get a direct reference to it. References are not revocable. Once you introduce an object, you cannot ask it to forget it. Or you can ask it, but you can't depend on it honoring your request. So the guest object has a reference to an agency object. the guest asks for an introduction to the powerful object. But the agency object instead makes a facet and gives that to the guest. The facet might be a simple pass-through. So the guest thinks it's talking to the powerful object, but it's actually talking to the facet. And at any time, the agency can send a message to the facet telling it to disable itself. It forgets its access to the powerful object, and that facet is now useless to the guest. So that's a way of accomplishing revocation. A facet can mark requests so that the powerful object can know where the request came from. So we have a facet which will put a stamp on everything that it receives as it passes it on. So we can determine where the request came from. So facets can be very expressive. They're very easy to construct. They are lightweight. They provide attenuation or power reduction. We can get revocation, notification, and delegation. And it turns out the best object-oriented programming patterns are also capability patterns. So sometimes when you're designing an object system and you're trying to figure out where the stuff goes, does this go in that class or that class, and you're trying to figure it out, it's really easy to get that wrong, and it's one of the biggest hazards in object-oriented programming. But if you think about it in terms of capabilities, what is the least amount of capability this guy needs to do its work, and use that to determine where everything goes, you get the right answer. So it actually makes it easier to design systems, not harder. So the thing we want to avoid is confusion, because confusion is when a program appears to do one thing and it does something else. We also call that bugs, but it's also a security exploit, that if our code can be made to do something that we don't expect it to be able to do, that's probably a security hazard. So confusion aids the enemy. We want to eliminate as much confusion from our system, from our code, as possible. Because with great complexity comes great confusion. So we want to keep our code as simple and clean as possible. Because only if the code is simple and clean can we reason about it correctly. If we can't reason about it correctly, then we are confused about it, and it's probably wrong. So it turns out good code is ultimately cheaper to produce than bad code. So you should just write good code all the time. There's no excuse not to. Good code is easier to reason about. Code that is difficult to reason about is more likely to be problematic. We should have strict conformance to style rules, which means when we're writing in JavaScript, everything we run should pass JSLint without warnings or exceptions. Now, a lot of people don't like that because it's hard and it makes them cry. But it's that important. Our code needs to be at that level of quality. We don't want to be turning off checks which could result in security exploits. You should never trust a machine that is not under your absolute control. And I don't even trust all of those. But for sure, you should never trust the browser. The browser cannot and will not protect your interests. You need to properly filter and validate all input. You need to properly encode all output. Context is everything. Everything has to be properly encoded and filtered for the correct context. So let me tell you a story about trusting the browser. This is a true story. Some years ago, not that many years ago, a friend of mine who worked at Yahoo, he worked somewhere in the Valley. Doesn't matter where he worked. He went to China for a vacation. And it's very expensive flying to China, so he bought a coach ticket. But he also realized it's a really long and uncomfortable flight. It'd be much nicer to go first class. So he went to the airline's website to see if first class upgrades were available, and they were. And you needed to have a certain number of upgrade certificates in order to qualify for the upgrade, and the number that he had was 0 because he didn't fly with them very often. And he was very discouraged until he opened his debugger and he found the variable that contained his number of certificates. And he flew first class to China. True story. They've since fixed the site. The reason that worked was the guys who developed that website assumed that a certain URL could only be generated if a particular set of facts were true. And they were depending on the browser to enforce that. And it turns out you can't depend on the browser to do that. You have to have, the server has to do that stuff. And that's why he was able to fly to China. So when e-commerce first started on the web, not all that long ago, the first e-commerce sites, we hadn't figured out how to scale websites yet. So all this stuff was happening in one box, and they were getting overloaded, and they couldn't handle it. And then JavaScript comes out, and they think, oh, great, we can offload a lot of processing onto the browser. So they allowed the browser to do all the work of creating an order, of summing it up and figuring out the tax and all of that stuff. And then it just sends back a form which they just send out for fulfillment. And some people figured out that if you know how to type a URL, you could order anything you want, and you could decide how much you want to pay for it. So the advantage of having code in the browser wasn't to offload the server, it was to provide a better user experience. That if we do input validation on the browser, then we get a much nicer way of creating a dialogue with the user to help them create a correct form, rather than having to go back to the server, and then you get another page thrown in your face, and then you have to deal with that. So the server still has to test everything. And that's one of the advantages of having JavaScript on both ends of the network, that it's possible to have exactly the same code doing the vetting, and that way there'll be no confusion attacks, whereas one thing will accept some things and the other will accept a different set, and maybe something can sneak through. So this, to give you an example, this is the simplest XSS attack I've been able to find. So the trick is you have to get your victim to click on a URL, which will go to your site. And it's got this crazy looking file name that's got angle brackets and stuff like that in it. And you think, well, nobody would ever click on a URL that looks like that. And the truth is, in fact, yeah, a lot of people, you've probably done it. And if they won't click on that, a bit.ly code or a QR code, there are lots of ways you can get people to go to something without seeing where they're going. And it used to be that by default, web servers would simply take the unfound file name, stick it in the middle of a document, and send it back. Except in HTML position, this becomes a script tag, which will load some code, which will then load additional code from the world's evilest site, and you've lost. So their script will run with the authority of your site. They have access to your local storage, your cookies. They're using your SSL certificate, all of that stuff they've won. And if the user was expecting to go to your site, they're actually running their code, so the page can ask for the password, and the user goes, oh, it's okay, good. So that's pretty awful. And it turns out most XSS attacks are variations on this, where you're taking something and putting it into a context where it's given capabilities that it shouldn't have. And the way you deal with all of those problems is exactly the same. You need to properly filter the stuff that you receive from the browser, and you need to properly encode the stuff that you're sending back to the browser. If you do that correctly in all cases, attacks like this, all the probably millions of variations on this attack now, none of them can happen. So you need to do that. Confusion can also come from concatenation. Templating isn't the only thing that can go wrong. So for example, when you're building JSON text, you should never, ever build JSON text by concatenating together strings. You should always use a JSON encoder, a JSON writer, do it right. In fact, all the libraries provide much nicer ways of creating JSON text. I would kind of like to get rid of the plus operator in JavaScript. First, it doesn't add very well, but that's for another time. So this used to be a source of insecurity. Why would anybody do that? Someone goes to management and says, we need to fix this thing because we could get attacked. And management goes, why would they do that? We now know why they will do that. They will do it simply because we didn't prevent it. So if we make it possible to attack our systems, they will. And if you have a site which somehow deals in valuable stuff, you'll pay them to attack you. And you'll continue to pay them to attack you until you figure out how they're attacking you and try to turn it off. So we've given them a financial incentive to attack our systems. That's why they'll do it. Finally, the most avoidable source of insecurity is mismanagement. I heard a snicker from the audience, which causes me to think there's more truth in this slide than... Anyway, I'll tell the story. So it sometimes happens where there'll be a manager who will ignore concerns about security. In fact, will tell people, we need to slip this past our security experts because we need to make this milestone. We have to have this date. We have these commitments. I've got a bonus on the line. We're going to make this. And we can't let that happen anymore. If you ever see that happening, you need to rat them out. You need to go to senior management, if necessary, go to the CEO and the board, tell them this is happening, because upper management has finally figured out we can't tolerate this stuff, but somehow it hasn't gotten to middle management yet. So, you need to do that. And that's the end. Thank you. That's principles of security. Thank you. I'm very happy that we have some time for questions. So, yes. These slides are available. Go to crockford.com/pp for PowerPoint. Crockford.com/pp. Yes.
Frameworks like React or virtual DOMs that release HTML
Yeah, I was asking if frameworks like React with their virtual DOMs, do they provide relief for these sorts of hazards? I don't rightly know. I don't know. Anybody else? Yeah.
Yeah. When sort of managing the code problem, do you budget time for security into it, or you just assume security is built in, just write through the code, just like you said?
Yeah. So I'd like to have daily code readings. So every day, I call them dailies. We'll look at the code that we wrote yesterday, and we'll review everything that's going on. And part of that code reading is looking for security issues. So it's every day.